Welcome to lecture number 21 of this course on nonlinear structural analysis, theory and applications. Let us recall what we did in the previous lectures. So, we have been looking at stress strain response of various materials, and also the models that we are studying can be used to model the force deformation response of structural components. Like I mentioned in the previous lecture, that the hysteretic models are classified into two types, polygonal hysteretic models and smooth hysteretic models. So, we have looked at some polygonal hysteretic model or PHM and some smooth hysteretic models, right. But we have not yet discussed anything about concrete as a material. So, in this lecture, we will be talking about models that can be used to model behavior of concrete, the stress strain response of concrete, and we will see in the next topic of the course how do we use this concrete material model to perform analysis at the cross section level of a member. Okay. So, we will be talking about one model in detail, and then I will introduce you very briefly about another model. There are many other models. Okay. So, first let us begin our discussion with the stress strain curve of concrete that we use in our Indian code IS 456-2000. Okay. How do we model the stress strain for design purpose? Well, we use FC. The stress in concrete is FCK, the characteristic cube strength, multiplied by 2 into epsilon c by epsilon 0 minus epsilon c by epsilon 0 whole square. So, which is nothing but a parabolic relationship. If I show you schematically, my vertical axis is FC over FCK normalized, so that this is going to unity. Okay. So, from here to here is parabolic, that means this is epsilon naught. Okay. Epsilon naught is 0.002, right. So, up to this you have a parabolic relationship, and then in our code we assume this is constant, which is given by FCK. Okay. So, FCK and FC prime is what? Characteristic cylinder strength. They are related, approximately FCK is about 1.25 times the FC prime. Okay. So, for design purpose what we do, we take only 85% of FC prime. That means, if I go from here to here 0.85 FC prime, then what I get in terms of FCK, it is going to be 0.67 FCK. Okay. That means 0.85 divided by 1.25, that is 0.67 FCK. And then on top of this, we apply a partial safety factors for material equal to 1.5, that gives us 0.447 FCK. And this is the stress strain curve that we use for designing concrete structures. Now, what we want to look at, models, stress strain models to simulate behavior of reinforced concrete structure under cyclic loading. That is the objective. Okay. So, before we get to the models, let us talk about little bit more about the stress strain curves for unconfined and confined concrete. Here I am showing you stress versus strain for 3 different grade of concrete. As you can see, this is 20 MPa. So, this is about 20 MPa, this is close to 40 and this is close to 60 MPa. So, 3 different grade of concrete stress strain obtained experimentally under uniaxial compression. What do we notice? Well, we notice a few things. First is as the strength of concrete increases, the strain at peak stress, for example, this is the strain at peak stress for this grade of concrete. This is the strain at peak stress for this grade, which is, let us say, close to 40 MPa. This is the strain at peak stress for this grade of concrete. What do you see? Well, this strain is reducing, and also we see that the strain at crushing for this lowest grade is here, then it is here, and then it is here. The crushing strain is also reducing as the grade of concrete increases. Okay. That is one observation. Then the concrete stress strain curve is hydrostatic pressure dependent. In other words, it depends on the confining pressure. So, just to give you an example, or just to explain to you in a layman language, I always take this example. Let us say you have a packet full of sand, right. If you pour it on the ground and apply some load, let us say you stand on it, what will happen? The sand will spread without offering pretty much any resistance to you, right. On the other hand, you keep that same sand within a packet, within a bag, and then you apply some load, you sit on it, you stand on it, of course, it is not going to spread easily, it is going to offer you reaction, right. Why is that happening? What is the bag doing? Well, the bag is applying a confining pressure, it is not allowing the material to spread, right. It is applying a confining pressure. Okay. So, the behavior of materials like sand, soil and concrete are dependent on the behavior is dependent on the confining pressure, or you can say hydrostatic pressure. When we go to multi-axial models, okay, we will talk about multi-axial stress strain response, then we will talk about what is hydrostatic pressure, but for now let us understand that the behavior of concrete depends on the confining pressure. Okay. To show you with experimental data, what I am showing here is stress versus strain, okay, average strain for 3 different grade of concrete. One is plotted starting at 0, the other one is plotted starting at 0.01 and this is 0.02. So, that all of them can be put in the same figure. And what is this? This is stress strain curve of concrete cylinder 150 mm diameter, 300 mm high, which is confined by 6.5 mm dia mild steel circular spiral. Now, what they have done? They have varied the pitch. Pitch means the distance between the two consecutive spiral, right. So, for example, for this curve, for this stress strain curve, the pitch is 30 millimeter. For the same grade of concrete, for this one, the pitch is, I think it is 45. Okay. And then for the same grade of concrete, for this one the pitch is 60, for this one this is 90, this is 120 and this is infinity, meaning that there is pretty much no spiral reinforcement. Okay. What do you see? Well, there is a huge change for the same grade of concrete, there is a huge change in terms of the strength and the ductility. That means, the ductility is the ability of the material to deform inelastically. Okay. In this case, it is able to inelastically deform and take much larger compressive strain. Okay. The same thing happens for this grade of concrete as well as this grade of concrete, right. So, therefore, the behavior of concrete depends very much on the confining pressure, and when we create models, we should keep this in mind. Okay. So, that is what I have summarized, that the confinement or hydrostatic pressure increases both strength and ductility or the strain capacity of concrete material. Okay. Now, how do we provide confinement? Little bit more on that. So, if we provide spiral or circular reinforcement in a circular concrete cross section, this is most effective. Imagine, just like I was giving an example of a bag full of sand. Okay. When it is circular, you stand on it, then it is applying uniform pressure, outward, right. And then this entire concrete in this case is actually confined. Okay. Very effective, right. You can cut a free body diagram and calculate what are the forces or the stresses in the confining reinforcement and so on. On the other hand, if you take a square hoop, right, this is a square hoop, then this entire cross section is not so well confined as compared to a circular cross section. Why? Because the moment it is square, you apply load, it is trying to, the hoop is trying to bend outward, isn't it? So, that means there will be an arch action, so like this, and then this region, this hatched region, this region of concrete is not so well confined. It is somewhere between unconfined and confined. It is not so well confined, but the white region inside, this region is well confined. Okay. So, that means, because the concrete stress strain depends on confinement, we have to create different models for confined concrete and unconfined concrete. So, pretty much the confined concrete is for within this, and the concrete that is outside the stirrup, that means the cover concrete, will be treated as unconfined concrete. Okay. So, with that introduction, let us now look into the model that was originally proposed by Kent and Park and was modified by Scott et al. In 1982. So, this model is often called Kent-Scott-Park model or modified Kent-Park model. What is the equation? Well, the equation is very similar to what we have seen in our IS 456. So, concrete stress is equal to Kc, a coefficient, multiplied by Fc prime. These are all written in terms of the characteristic cylinder strength. Okay. So, Fc prime multiplied by Kc into this parabolic equation, right, where epsilon 0 is the strain at the peak stress. Okay. In our Indian code, for design purpose, this was 0.002 and this was simply Fck. Okay. So, that is when epsilon c is less than equal to epsilon 0. Then after that, for design purpose, we assumed it is constant, but actually as you have seen, if you go back, as you have seen, all these curves are kind of coming down, right, depending on the confinement. So, to model that, what is being done, this equation is used with a residual strength which is given by 20% of Kc into Fc prime, that means 20% of this magnitude. Okay. What is this parameter Z? Let us look into it. So, this is an example stress strain response, okay, taking realistic values, and the vertical axis is in KSI, that is Kips per square inch. You can always convert it to MPa. Okay. So, this red is the unconfined concrete, this is a 4 KSI concrete, and when I consider certain confinement, then I get some value of Kc, and this is the strength of the confined concrete. What is the change in terms of the after the peak stress? Well, this is reducing at a much slower rate as opposed to the unconfined concrete. Okay. And this residual is 0.2 times Kc into Fc prime. Now, how do we determine Kc? As we know, it should depend on the confinement, right. So, epsilon 0 also depends on Kc. So, this epsilon 0 for the unconfined is 0.002, just like our Indian code. Considering confinement, it is 0.002 into Kc. Now, what is Kc? Well, Kc is 1 plus a quantity which accounts for the effect of confinement. What is rho s? I will explain. Rho s is the ratio in terms of volume of steel, confining steel, and the concrete, and it is better understood through an example which I shall show. And Fyh is the yield strength of the hoop reinforcement, and Fc prime is the characteristic cylinder strength of concrete. And Z is given by this empirical equation where Fc prime must be in MPa, because there are numbers which has no unit. So, therefore, this is purely empirical equation. You must enter this with Fc prime in MPa. Okay. What are the parameters involved? There is H prime, there is rho s, and there is SH. We shall see what are these parameters through an example. Okay. So, let us take an example. I have a 2-story building which I have designed for one of my paper, which is listed here, and the cross section of the column is something like this, where I have bar numbers are all as per US standard. Okay. So, I have got 8 longitudinal reinforcement of number 9, which is of not much use in this case, because we are interested only in the concrete. And then this stirrup, diamond shaped stirrup is number 3 bar at 4 inch in confining zone and number 3 at 6 inch elsewhere. What is confining zone? Well, if you are familiar with earthquake resistant design, you would know that here towards the base of the column, and here design code says that you have to specify closely spaced stirrup, which is called the confining zone, right. So, in this region the spacing is 4 inch for the diamond, and elsewhere it is 6 inch, and for this outer stirrup it is 4 inch again, but it is number 4 bar, and elsewhere it is 6 inch and number 4 bar. Okay. So, the strength of concrete in this case is 4 KSI, which is in MPa 27.6 MPa. Yield strength of hoop is 60 KSI steel, so 413.7 MPa, and the clear cover I took 1.5 inch, which is 31.1 millimeter. And for the hoop reinforcement, number 3 bar means it has a diameter of 3/8 inch, and number 4 has a diameter 4/8 inch, and these are the cross sectional area of the bars which we will need to calculate rho s. Okay. So, now let us consider the core concrete. So, in this case honestly speaking, this will be the arch action, okay. This will be the arch action, and then the concrete inside this will be confined, right. So, we want to determine this core concrete in the confining zone. Confining zone means in this region or in this region. Why? Because the spacing of the stirrup is changing from this region to this region. Okay. So, I am looking at the core concrete in the confining zone. Okay. So, how do I calculate the rho s? So, first we have to calculate the volume of core concrete. What I am doing, let me draw. So, let me draw, this is my column, okay. I am drawing a longitudinal section, and these are my longitudinal reinforcement which I do not need to worry about, and let us say these are my, I should show like this, these are my stirrups, right. I am just showing 3 stirrups. What is the spacing? Well, the spacing of the stirrup is, let us say, S, which I know from my design, right. So, that means if I consider from this center to this center, what is the spacing? Well, that is also equal to S. So, what is the volume of concrete in this region? The volume of concrete is ACH, that is the area of concrete into this spacing S, right. What is ACH? ACH is 16, which is this dimension, 16 minus 2 into 1.5, 1.5 is the clear cover on each side, multiplied by 18, which is this dimension, minus 2 times the clear cover, okay, into 4. So, that means you are just subtracting for the clear cover, and this volume is the volume of concrete measured outside of the stirrup and between this. Okay. So, that is this volume 780 inch cube, right. Then what is the volume of stirrup in that region? So, if I go back in this portion, how much stirrup do I have? Well, I have only this, but that is I have a rectangular stirrup and a diamond stirrup. There are 2 stirrups in that volume. So, volume of number 4 hoops is the perimeter. How do I calculate 12.5? Well, 12.5 is the center of this stirrup to center of this stirrup is 14.5, and in this direction this to this is 12.5. Okay. Into 2, that gives me the perimeter multiplied by cross sectional area for number 4 hoop, that gives me 10.8 inch cube. Similarly, volume of number 3 hoops, which is this diamond shape. Okay. So, if you calculate using Pythagoras theorem from here to here, center to center, you will get 9.57 into 4. This is the cross sectional area, that is 4.21 inch cube. Okay. So, what is my rho s? The rho s is the volume of stirrup, these 2, okay, divided by the volume of concrete, which is 0.0192. Now, I can calculate what is my Kc. So, my Kc is 1 plus rho s into Fyh, which I know, Fc prime, that gives me 1.288. That means, there is 29% increase in the strength due to this confinement that I have taken, and also 29% increase in the strain corresponding to the peak stress, that means epsilon 0. Okay. Now, epsilon 0, like I said, 0.002 Kc, which is this much, right, and I can also calculate the residual strength, which is 0.2 into Kc into Fc prime, which is 7.10 MPa. And I can calculate also Z using that empirical equation. Everything is known except that I have to discuss what is H prime and what is SH. What is H prime? H prime is the width of concrete core measured outside of peripheral hoop. So, this is my outer hoop, right. So, what is H prime? The width of concrete core, that means here to here, is 13 inch, isn't it? Because 16 minus 1.5, 1.5, that is 3. So, that is 13 inch. This is the width, okay. And SH is the center to center spacing of hoops, the outer hoops, which is 4 inch. So, that is 101.3 mm, right. So, with that I calculate my Z for confined concrete 18.5, okay. Similarly, if I said rho s is equal to 0 for the unconfined concrete, because there is no stirrup, the concrete outside the stirrup is called unconfined concrete, right. So, then if I said that Kc is equal to 1, epsilon naught is 0.002 and Z is 299.9. That means, now you can plot this stress strain response for concrete, this is for the confined, this is for the unconfined. You see what is the change in the slope. So, this how quickly it is coming down. So, this is 299.9 and this is unity, as opposed to this is how much? This is 18.5. This is 18.5 and this is unity, right. You can see how rapidly this unconfined strength is reducing, okay. And this is how much? For the confined concrete we calculated it was 7.1 MPa, this is 7.1 MPa, and for the unconfined concrete we calculated this is 5.5 MPa, right. So, that defines my stress strain response under monotonic loading, right. How do I define the stress strain response under cyclic loading? When I have this concrete material, I am studying the response of a reinforced concrete member, be it a beam, be it a column, where I have concrete, I have steel and so on, and this is subjected to cyclic loading, right. So, how do I now determine the stress strain response for concrete under cyclic load? Okay, that is what we want to discuss. So, this is experimental data obtained by Carson et al. Okay. This is compression stress versus strain. If you look at this, this is the monotonic envelope. If you do a monotonic test, this is what you get. If you do a cyclic test, then the stress strain response is going something like this. It is going something like this, right. So, as you can see, there are few things that are happening here. One is cyclic stress strain curve is actually reaching the monotonic envelope. You see, it is reaching the monotonic envelope. This is number one observation. Number two observation, unloading and reloading. So, for example, from here this is unloaded, and when you are reloading, it is actually not following the same path. There is a small hysteresis, right. This is experimental data. Okay. There is a small hysteresis. It is unloading like that, going like this, and then like so, right. There is a small hysteresis. What else? At higher strains, significant degradation of unloading and reloading stiffness. For example, if I forget about this hysteresis and just join this line, okay, draw a line here. Now, if I draw at a higher strain this line here, what do you see? The stiffness for this curve versus that, there is a significant difference. At higher strain, the loading and unloading stiffness for concrete has reduced. Okay. So, with this observation, then we can define the hysteretic response under loading and unloading. It was done by Carson and Jirsa. I will talk about that. So, let us say this is my KCFC prime for confined concrete and this is the strain. Okay. So, this blue one is the monotonic envelope, right. Now, let us say you are at this point. How do you get that? Well, that comes from your applied strain history. So, at this point, let us say the material will now undergo unloading. So, the strain at this point is called epsilon r, okay, and then you unload it like this and come to a point epsilon p. The question is, how do you get epsilon p? Epsilon r is known to you. How do you get epsilon p? Okay. In such a manner that when you go to larger strain, this comes down like this, and again going back in this same path. So, this epsilon p is determined by this equation. Okay. So, it says unloading from a point on the envelope curve with strain epsilon r follows a straight line. That means, we are ignoring that small hysteresis that we are getting, that is ignored. Okay. So, epsilon r to a point epsilon p. How do I calculate epsilon p? Well, using this equation, where it is normalized by epsilon naught. What is epsilon naught? Epsilon naught is the strain corresponding to the peak stress. Okay. So, what we are doing? This is given by this first equation, which is parabolic. What is epsilon r? The point from which you are unloading the strain, which is again normalized. So, this is a parabolic equation, and it is valid when the epsilon r by epsilon naught is less than 2. Why it is not valid for this higher than 2? We shall see. Okay. So, this is one aspect, that epsilon p is now determined by this equation. Okay. Then that means once you know this point, you can calculate that point using the first equation. If your epsilon r by epsilon o is less than 2, if it is greater than 2, then you will be using the other equation. Okay. And you will see that epsilon p and epsilon r, how are they changing? I will show you a figure. Okay. And then that will capture this deterioration in the stiffness. Okay. Then tensile strength of concrete is neglected. That means Fc is equal to 0 if epsilon c is less than epsilon p. This is very interesting. That means you unload, let me go to that figure again. So, let us say from here you have unloaded and you have come to this point, right. So, you have come to this point, right. Then if you go in the negative direction, if you keep reducing the strain, what happens? So, you took the concrete up to this, unloaded, right, and then when you go in this direction, then the concrete has cracked, right, and there is no tensile strength. Although concrete shows some tensile strength, in this model we are ignoring it completely. Okay. So, there is no tensile strength, it goes like so. Okay. Then on reloading in compression, Fc is equal to 0 as long as epsilon c is less than or equal to epsilon p. What does it mean? Let me go back. That means crack remains open. Let me go back and explain. So, you were here, you unloaded to this point, now you are going in this direction to the left. When you are reloading, imagine you have a reinforced concrete beam, you are looking at a concrete point on top, right, and that cross section is subjected to reversal of moment. At some point that concrete, the point is under compression, at some point it is under tension. So, it is undergoing reversal of strain, right. So, you have gone like this. Now, when you are going in this direction, the concrete is assumed to remain cracked until the same point is reached. Okay. You go and then go like that, right. If you have come back like this, okay, then you will go here and then reload along this same path, not through this path, right. If epsilon c is greater than epsilon p, then only crack closes and reloading occurs along the previous unloading path, which is what I explained, that if you have unloaded along this path, you went like that, then you will be loading along this path only. If you have unloaded along that path, you went like this, you come back, you will be loading through this path only, no other path, okay, because the crack is remaining open up to this point, right. Equation 1 was proposed by Carson and Jirsa, as I was saying in this paper. It has a problem. The problem is it leads to negative unloading modulus for high values of epsilon r. Okay. What do I mean by that? If I look at this first equation, what we are doing, we are calculating epsilon p for a given value of epsilon r. Both are normalized by epsilon 0, that is fine. If we use this, when epsilon r is large, we are going to the right hand side, then epsilon p could be such that you can get a negative thing. That means, let us say you are unloading from here. Okay. So, this is your epsilon r. You calculate epsilon p, which happens to be here. That means, this is how you are unloading, which is a negative stiffness. That is the problem with the first equation. How do I know that is happening? I have done a very simple exercise. I have taken various values of epsilon r, of course normalized, and calculated using the first equation what is my epsilon p, right. So, that first equation plots like this, right. On the same figure, I have plotted a 45-degree straight line. What is happening on the 45-degree straight line? Epsilon r is equal to epsilon p. That is what the 45-degree straight line means. Now, this equation is telling me that if I exceed this epsilon r by epsilon naught ratio 6, then the first equation is going to give me epsilon p which is greater than epsilon r, because this is going above the 45-degree line. That means what I was explaining, that you are going to have this phenomena, epsilon p is greater than epsilon r. So, what Tosser et al. Did, they added the equation B, that is the second equation. How did they come up with that equation? They said, well, let us define an equation like this, which is kind of going tangent to that, okay, and we will take the first equation up to this, up to 2, and then we will follow this. By doing this, what I am ensuring that the loading stiffness will never be negative and it will keep on deteriorating, as you can see, because epsilon p is always less than epsilon r as we are below the 45-degree line. Okay. So, that is how this second equation, which is a linear variation, was considered, right. Now, I will briefly introduce you to another model of concrete that is given by Mander. Okay, it is called the Mander model. We have discussed in some detail the Kent-Scott-Park model or the modified Kent-Park model. The Mander model is improved, you can say, compared to the Kent-Park model. Okay. But in the interest of time, we will not be able to go through the entire thing. If you are using for research, then you can of course go to this paper. So, what is the idea? Very similar, that you are looking at compressive stress and this is the strain. So, this is the monotonic envelope. Here you can capture the hoop fracture which was not present in the Kent-Park model or modified Kent-Park model, and this is the behavior for the unconfined concrete. The strength of the unconfined concrete is defined by FCO, and for confined concrete it is FCC prime. The calculation of FCC prime is little bit involved, hence I am not going to go through, okay, but the stress strain response is given by this simple looking equation, where FCC prime is the strength of confined concrete, which you calculate by accounting for the amount of confinement that you have provided, and then x is nothing but the strain, concrete strain normalized by epsilon cc, which is the strain corresponding to the peak stress. And then there is this parameter r, which I will show you in the next slide, and epsilon cc is just like in the previous case, epsilon 0 was kc into 0.002. In the Mander model, what we are doing, in the Mander model, the strain is calculated as epsilon co, that is the strain corresponding to peak stress of the unconfined concrete, multiplied by this equation, where again you are considering the confined strength and this is unconfined strength. Okay. So, these variables are all defined, and epsilon co, just like the Kent-Park model, it is typically taken 0.002. Okay. What is this parameter r? R is the ratio of EC. EC is the modulus, the initial modulus, okay, divided by EC minus E secant. E secant is the this modulus, right. So, that is how R is defined. EC is taken to be 5000 square root FC O prime, very similar to our Indian code, where we take here FCK. E secant, like I said, is the slope of this line. So, FCC prime divided by epsilon cc. So, this is how the monotonic envelope is defined. If you are interested, you can go ahead and read this paper. In OpenSeas, there are many more concrete models. Okay. So, you can try with the basic understanding of the Kent-Park model, you can look at many other models. Okay. So, now let us summarize what we have discussed in this lecture. In this lecture, we have discussed the Kent-Park model, which in OpenSeas is called concrete 01 material model. Okay. How do we use it? Well, in the next topic, when we study reinforced concrete cross section subjected to axial force and bending moment, whether it is uniaxial moment or biaxial moment, whether it is cyclic or monotonic, we will be able to study using this concrete material model, right. And into some detail, we have studied how the cyclic response is modeled, how it is motivated by experimental data, and briefly introduced you to the Mander model, which is also quite popular. Okay. Now, I would say that this topic of hysteretic response of materials and components is kind of complete. We will come back to the pinching and degrading type of hysteretic response later on in the course. Okay. With that, we will move on to the next lecture, where we will be studying inelastic behavior of cross section, be it a reinforced concrete, be it a steel, or we can also take concrete and steel composite cross section, that is what is called CFST. Okay. That is a concrete filled steel tube. Okay. With that, we will stop here in this lecture, and these are the references that we have used. Okay. That is all. Thank you.